Okay, thanks a lot. So my name is Brad Nemenich, and I'm here with Bryant Nelson. We're both from IBM, and we work on Watson machine learning. And today we're going to give a discussion on how to do distributed deep learning on Summit. So deep learning training jobs actually run particularly well on Summit due to having a lot of fast GPUs and a high-speed interconnect between all nodes. So Summit is a great place to do deep learning jobs, but there are some roadblocks to getting started, and that's where the Watson Machine Learning CE product will come in and try to help out on that. So some of these roadblocks are that there's lots of different deep learning frameworks, and sometimes it can be hard to even choose which ones to use. And they can also be difficult to build in general, and then lots of times you need a special build for it to actually run well on Summit. And a typical deep learning job actually relies on many, many different packages and components. Most of them are Python-based, so there's lots of different Python packages you might need. They might also include different C libraries, and all the different packages might need different versions of different packages. So it can be kind of difficult to install all of these dependencies in a single environment. Also, these frameworks are all very new. Most of them have were created just a few years ago. And because of this, they're constantly changing. There might not be as much documentation available as you might expect with other more common products. So troubleshooting can be kind of difficult, particularly during the build phase. And it can also be difficult to run these deep learning jobs on a distributed cluster. Most of them are designed and really tested on single nodes and even single GPUs on a single node. So it can be kind of difficult to get your deep learning jobs running in a cluster, especially a large cluster like Summit. So this is where Watson Machine Learning CE comes in, and we're going to try to address all of those problems that I mentioned earlier. We provide a curated set of pre-built deep learning packages, and those have all been optimized to run well on IBM Power Systems with NVIDIA GPUs, which is what Summit is. So essentially, these have all been built to run well on Summit. So you won't have to worry about building any of these packages. You won't have to worry about picking which version of these packages are because we've already done that for you. And all of these packages have been verified to work well within the same environment. So that's really cool. That means you don't have to worry about picking the right version of different Python packages. We've done that for you. We've made sure that you could even use TensorFlow and PyTorch within the same environment, which can be useful for different testing purposes. And all of these packages are fully supported on Summit by IBM. So if you run into any kind of problems, you can go through the normal processes at ORNL, and those will eventually get to us at IBM, and we'll be able to help out with any issues you might have with Watson Machine Learning CE. And it includes IBM's distributed deep learning package, and this provides easy tools that make it easy to launch jobs on large clusters, and they've been tuned well to run on Summit on up to 950 nodes right now. So currently, you can only run this on up to 950 nodes, but that might change sometime in the future. And Watson Machine Learning CE also provides other unique features from IBM that you won't be able to get in any other open source package, such as large model support and SnapML, which I'll go over briefly a little later in the presentation. So these are some of the big name packages that you'll be getting with Watson Machine Learning CE. And these are all kind of the most commonly used deep learning frameworks, as well as many frameworks that you would use for machine learning. So some of the big ones are TensorFlow and Caffe and PyTorch, but we also provide some of the lower level libraries that these big packages rely on, such as OpenBLAS and Bazel. And then we have machine learning packages such as IBM SnapML, but so Rapids and scikit-learn. And here's a list of some of the packages that you'll be getting with Watson Machine Learning CE 1.6.1, as well as their version numbers. Very soon there'll be a version 1.6.2, which will update a lot of these version numbers to the most recent ones. One thing I'd like to call out that's slightly different than the normal CE packaging is we also include a Horovod package that's built with IBM's DDL, and that's only on Summit. So you won't get that outside of Summit if you're trying to use this on a workstation, but all these other ones. So I do want to go over a couple of our unique features. The first one is our large model supports. And what that does is it'll, the issue that it's trying to solve is that GPUs have a limited amount of memory compared to a CPU, and there's not really a concept of paging. Sorry, someone's probably on. There's a lot of noise in the background. So there's not really a concept of paging on a GPU. So right now, if you run a job that uses too much memory on your GPU, you will get out of memory errors.
Shazeen, can you mute? It sounds the noise is coming from Shazeen.
Yep, just a second.
Great, thanks. So what large model support will do is it will actually seamlessly move layers from the GPU and the CPU, from the GPU to the CPU and back again to overcome some of these GPU memory limits. And all of this is done in a really efficient way. And that allows for training of deeper models or training with higher resolution data or training with larger batch sizes. And this works particularly well when you have NVLink 2 connections between the CPU and the GPU, like you do on Summit nodes and other IBM power systems. That means that you actually have minimal overhead for all of this data swapping. So this is really cool. This will allow you to run models that you can't do on other systems without this large model support. And large model support is enabled in Watson Machine Learning CE's versions of TensorFlow, PyTorch, and Caffe. And if you want more information on this, you can follow this link, and these slides will be available after the presentation. Another unique feature of Watson Machine Learning CE is SnapML, and this is a package of parallel and accelerated machine learning algorithms. So this isn't really focused on deep learning. These are actually frameworks for machine learning. And it's packaged as an extension to scikit-learn. So if you've already got scripts that are using scikit-learn, you can easily start using these SnapML algorithms. And some of these can really increase performance based off of your standard SnapML algorithms, which are normally only run on, might only be run on a CPU. We have ones that can be run on GPUs, and they can be distributed. So we also provide some of other machine learning algorithms that come from Rapids, and we wrap those around our scikit-learn extension also. And as we go on, we keep adding more and more algorithms to this. So this is another cool feature that you get only with Watson Machine Learning CE. So Watson Machine Learning CE is packaged as a collection of Conda packages, which makes it really easy to use and set up different environments. A module for it actually exists already on Summit, so it's really easy to get started on Summit right now, and we'll go over that in a little bit on how to do that. But it's really easy to start using Watson Machine Learning CE on Summit. But it's also provided as a public Conda channel, so you can use it outside of Summit if you'd like. It'll be freely available through this public Conda channel. And we also have an x86 version of CE through this public Conda channel. And that can be really nice because you can start developing with the same environment on your workstation. And then once it's kind of ready to run on Summit, you can move your scripts over to Summit and know that you'll be running on the same exact environment that you had on your workstation. So that can make it really easy to move from your workstation to Summit. So the actual module on Summit is called IBM-WML-CE. So you can get access to this really easily by just typing module load IBM-WML-CE. And when you load this module, it'll actually activate a Conda environment that has all of Watson Machine Learning CE installed in it. It will also set up default Conda channels to point to both our public Conda channel and a special local Conda channel on Summit that has Summit-specific packages installed on it. So even if you're planning on just using the public Conda channel, we recommend loading this module so that you get the Summit-specific packages. So you can either just use the activated Conda environment or create your own, and we have kind of instructions for how to do either one of those on the Summit documentation that we'll point to later on. So this screen is just showing how easy it is to start using WML-CE on Summit. So on this screen, I've launched an interactive shell, and then all I've done is a module load IBM-WML-CE, and now I can run a Python script that might be using our version of TensorFlow or PyTorch. And in the green, you can see that the Conda environment has been activated. So that's the name of the Conda environment, IBM-WML-CE-1.6.1. If you want to install other packages into your environment that aren't part of Watson Machine Learning CE, you'll have to create your own Conda environment. and that's because the one that's installed on Summit is in a write-only area, or sorry, a read-only area. So in order to do that, it's pretty easy. You just, you still want to load the module so that you've got the Conda channels set up correctly. Then you just clone the current Conda environment, and that'll pull in everything that's already in the module, and it will clone that onto your home directory by default. And then all you have to do is activate the new environment that you just cloned. If you want to store this environment, and then from there you can do Conda installs or pip installs to add more packages that you might need. And if you want more information on how to do this, you can follow this link. We give more detailed guidelines on what you should be doing. So now I'm going to hand it over to Bryant, and he is going to talk about how to actually do distributed deep learning.
Yep. So thanks. So I'll start with a kind of basic overview of the kind of distributed deep learning that we primarily do on Summit, and then get into how to use IBM's DDL to actually do that distributed deep learning on Summit. So first, to give some context, so the primary type of distributed deep learning we do on Summit is data parallel distributed deep learning. Specifically, we do a synchronous all-to-all data parallel distributed GPU deep learning. So in this type of deep learning, or distributed deep learning, there's a process created for each GPU in the cluster. So in Summit nodes, you get 6 processes per node, basically. And here, each of these processes, so each GPU maintains a complete copy of the model, all of the weights, all of the biases. And during training, the mini-batch is spread across all of the processes. So each process is actually using different input data during the training. And then after a signal pass through the model, all of the processes sync together and average their gradients. And then as they go back, they update their weights with those average gradients, so that after each iteration, all models on each GPU should be exactly the same. They all train on different data, average their gradients, and then update their weights together. So they're kind of maintaining their models even though they're all training on different data. So I like to point out some different tools that are used in distributed deep learning, just so that people, sometimes there's some misconceptions about which tools do what and what they're used for. So on the left here, I have lined out communication libraries, and on the right, integration. So common communication libraries are things like MPI, NCCL, IBM's DDL library. These are the tools that actually do the transfer of data. On the other side, we have what I call integrations or frameworks. Here you have things like TensorFlow's distribution strategies. You have Horovod. You also, IBM DDL also provides some integrations. PyTorch, things like PyTorch provide native integrations and things like that. So some more detail. So like I said, these communication libraries, they're the tools that provide the actual communication functions, or the functions that do the communication. These are mostly things like all reduce and broadcast. So some of these tools are, you have MPI, that's your classic distributed computing communication library. It's still used for distributed deep learning in some places, but not as often anymore with things like NCCL. NCCL is NVIDIA's GPU to GPU communication library, which since NCCL 2 has been has supported between node communication as well. And then what we have is IBM's DDL tool. So that provides a slightly more advanced, topology-aware all reduce. It optimally divides communication across fabric hierarchies and actually utilizes different communication protocols at different levels of that hierarchy. And it's built on top of other communication tools like NCCL and MPI. On the other hand, you have the integration frameworks. And these are the tools and libraries which actually integrate with the deep learning frameworks or are deep learning frameworks themselves. I like to point out the differences here, mostly to focus on Horovod. Horovod itself is an integration into deep learning frameworks. It doesn't provide the communication libraries. It's not a communication library itself. Horovod uses things like Nickel or MTI or on Summit DDL to do its communication. It provides the integration into the frameworks and does some smarts to make the communication more optimized. And then you have things like TensorFlow's distribution strategies, PyTorch's native distributed integrations, and IBM DDL provides some distributed integrations as well into things like TensorFlow and Caffe. All right, so now I'm going to give a little more information on IBM's DDL tool itself. So IBM DDL provides, first, it provides some C and Python libraries directly that utilize the MPI and Nickel library. So if you are low level enough that you actually want to do direct distributed communications, you can actually access DDL C and Python libraries and do that yourself. We also provide framework integrations into TensorFlow, Caffe, PyTorch, and Horovod. And we also, DDL also provides a tool for launching jobs across a cluster that we call DDL Run. The example there shows it launching on a few different servers just using DDL Run. On Summit, it's even simpler because we have some information about the cluster. But basically, it simplifies the launching of distributed deep learning jobs. What DDL really provides is an all-reduce that uses cluster layout knowledge to perform reductions in a certain order to optimize performance. So it orders these communications in such a way that it knows about the hierarchy of the cluster and orders these communications in such a way that it optimizes that communication. All right, so the next thing we're going to step through is a simple example converting or taking a TF-Keras model and actually making changes to it so that it will run distributed using DDL. And I have a link here to the original script if you'd like to go and look at that yourself. So the first step, and I point out here that this is the only necessary step to enable distributed training with DDL is to import the DDL library. If you import DDL, you can launch your script with DDL Run, and it will run distributed. It may not do all the right stuff, but it will run distributed with importing DDL. The next most important step is to split the training data. So we mentioned that distributed deep learning or data parallel distributed deep learning, each GPU needs to work on different data. So for that to happen, you have to split the training data. So usually, so if the training works by iterating over all the data, kind of in a loop, then if that's what your script does, then you need to be sure that you split your data and that each process iterates over equal sections of the data. However, if your script works by maybe shuffling the data, maybe you have a large data set and you shuffle the data and randomly sample that data set, then it may not be necessary to split your data. You just need to make sure that each process starts with a different seed. The key point being here that you want each process to be looking at different pieces of the data. Otherwise, they're all doing the same training, and averaging doesn't do anything. So in our example, we split the data set by using NumPy and some of the built-in DDL functions. We see using the np.arraySplit. We have ddl.size and ddl.rank. So here we're splitting both the training data and the testing data. In this case, we needed to split the testing data too, and it's for a deeper dive, but anybody who's going to be doing this, especially with Keras, if you have on-the-fly validation, it's important to split your test data also. Because while you split your training data, if you're doing on-the-fly validation, that validation quickly becomes the bottleneck if you're not also splitting that test data. All right. The third thing you'll have to do to use DDL or you might have to do is modify the hyperparameters. So once you start distributing your training and scaling up to more nodes, usually the hyperparameters that were chosen for a single node will not work once you go multi-node. The things like the batch size, once you start scaling out, your batch size gets much larger. That affects things like your learning rate, your learning rate schedule, your alphas and your betas. Any hyperparameters that you have tuned for a single node should probably be revisited and retuned for multi-node. In the example we have here, the only hyperparameter we changed was the learning rate. So since the batch size was getting larger, we scaled the learning rate to basically offset that increase in batch size to kind of keep it doing the same thing. And this will work on small scale if we took this example to large scale distribution, that wouldn't keep working. We'd have to look at some other way to offset that. And the final thing you have to do, this is a Keras specific consideration, is to add the callbacks. So DDL provides two Keras callbacks, the DDL callback and the global variables callback. The DDL callback should always be the first callback in the list, and it's responsible for synchronizing the Keras metrics so that each node reports the same metrics during execution. And the global variables callback should always be the last callback in the callbacks list, and it actually initializes all of the global variables to the same value. Sometimes Keras does some funny initialization, and this callback makes sure that all that initialization happens the same on each node. Because again, we want the same model on each GPU. All right. And then to execute, like I said, we use DDL run. Here we can see DDL run giving it a host list of a single host at DLW03 and executing. So in this example, we're actually executing the TFC and benchmark script. We see giving a single GPU getting something like 1,200 images per second. And on the next step, we see upping it to 10 nodes, DLW4 through 13, and getting 12,000 images per second. So 10 times about the numbers, the images per second. So both of those were running the same script. The only change was our host list. And in our next example, this is even easier on Summit. So we've made some changes, some Summit-specific improvements to DDL run. So on Summit, here we see a vsub script with your normal vsub tags up at the top, your wall time, your project, things like that. But you also see we're specifying 10 nodes. So the number of nodes is 10. You see we do a module load, IBM WMLCE, and then DDL run, Python, and our script. So you notice we're not specifying host lists. We're not saying what host to run on. It's mentioned anywhere. DDL run will actually, it integrates with LSF and things like JS run and goes and grabs what nodes to run on and distributes across those automatically. So in our case, in Summit, the only change we need to make to run on a different number of nodes is to change that node count. Everything else is handled for us automatically, which is really nice. And we see good scaling on when using these tools. So here we have a scaling chart running the TF CNN benchmark script on ResNet 50 on synthetic data up to 6,912 GPUs, so 1,152 GPUs, and we see basically over 90% scaling all the way up to those 1,000 GPUs, and we see that here plotted against the ideal scaling. Right. And we mentioned before, the example we showed here was using TF Keras. We really recommend, especially for TensorFlow, using Horovod. That's what we've seen the best performance with on Summit is using Horovod for our integration method. And so on the Summit module, we provide a Horovod already built with the IBM DDL backend. And that should work with existing versions or existing scripts that use Horovod. You may have to keep in mind if you did some tricky things about data layout and things like that. You may need to keep in mind that might need to be revisited. But for the most part, Forvod script should work out of the box with the WMLCE module on Summit. So real quick before we get into that, I would like to show a demo of it running on Summit just so that you can see the steps that are needed to run on Summit. So I have a pre-recorded demo here running the TF-CNN benchmark script on Summit. And I'm only running on 2 nodes. The main point of this is to just show what the script looks like. You can see here we're loading the IBM WMLCE module. And again, our DDL run script has our DDL run command really doesn't make any reference to nodes or hosts or anything like that. The only thing we specify is the number of nodes is 2. We submit that to the scheduler, go through and watch it, make sure it gets kicked off. Then we'll watch the output as it scrolls by. Takes it just a little while. If you're ever interested or you need to do some troubleshooting, we mentioned this in documentation. That's the command that DDL run is putting together for us. So it's doing a lot of work for us. And then, let's see. There we go. Finally, we have the output, and we see so this is 2 nodes, so that's 12 processes. We actually have 12 processes reporting their output there at the end. Also reporting the total images per second. And yeah, that's all that's needed to run a distributed job on Summit using IBM WMLCE. Right. We'll switch back over and finish this up. So a couple concepts. We're not going to go very deep into these. They really need a little more time to cover in detail each of them individually. But some things to keep in mind when working with distributed jobs on Summit. First is the batch size. Once a lot of hyperparameters, a lot of models are tuned for specific batch sizes or with specific batch sizes in mind, and the moment you start changing those, things don't converge right, or they start converging to the wrong things. So it's important, or maybe it's not possible to run on a larger batch size because you only have so many input samples. So it's important to keep in mind that as you scale using data parallel distribution, that your batch size goes up proportionally to the number of GPUs that you're running on. So you need to keep in mind that hyperparameters may need to be tuned, batch sizes may need to be reevaluated, models may need to be modified, because again, you start to run on large batch sizes very quickly as you scale up. And kind of hand in hand with that is the learning rate and your other hyperparameters. All of those, as your batch size gets larger, you need to revisit your hyperparameters. Another thing to keep in mind with data parallel distribution is your batch norm. So batch norm works, the batch norm layer works by viewing it expects to view the entire batch and do some calculations. The problem is that each process, each CPU doesn't see the entire batch during training. It only sees its part of the batch. So that causes batch norm to calculate the wrong values and do some incorrect things. A lot of times that's okay. And things just tend to work if the percentage of your local batch is big enough compared to the global batch, or you just have enough samples. That tends to work, but that's something to keep in mind that if you start seeing some weird stuff, check into whether or not you're using batch norm, and you may need to look into other methods of normalization. I mentioned earlier the on-the-fly validation. That can quickly become a bottleneck, so be sure that you keep that in mind and turn that off, or handle that another way, split your test data, something like that. And another really big one, especially once you start scaling up at all, is data pipelining. So where you're storing your data, what storage system you're using to store your data, how you're loading that, how you're modifying that. If you're going from a single process on a single block to 6 processes on a single block, you could quickly overload your CPU if you're doing pre-processing. You could overload your file system if you're loading off a file. So all of those you need to keep in mind when scaling your distributed deep learning. And that's basically all that we're going to talk about. The documentation is available at that link, or if you just go to Oak Ridge Documentations and navigate through software, the software layer, you'll find that. And then these are the points of contact for support. Those are also available on the Oak Ridge website. Those are the normal Oak Ridge support. Oh, yeah. And we will finish with bringing up the documentation. So that'll be a good getting started point. The documentation provides some good information, and then for using each of the frameworks individually, we link out to our standard documentation, things like that. That way you have a lot of resources to get started and a lot of information available.